Okay, so let's get started with the first chapter of Chem 107, Chemistry for Allied Health. In this case, we're looking at chapter 1, which concerns matter and measurements. Okay, so let's start off with the first foundational concept as part of our introduction to chemistry. So let's talk a little bit about chemistry and matter. So what is chemistry fundamentally? Chemistry focuses on the study of matter. It looks at the transformation of matter and the energy changes that accompany those transformations. Now, just to define some key terms, energy is the ability to do work or accomplish change. So an example of this, so accomplish change, one example of accomplishing change would be heating an object. Heating and cooling entails the transfer of energy. Now, matter is a very catch-all term. It's anything that takes up space, in other words, has volume, and has mass. So matter is essentially almost anything in our physical world. Anything that takes up space and has mass is matter. Now, a critical idea in chemistry is this idea that matter is composed of small fundamental particles that we call atoms, which is derived from this Greek idea or the Greek word for an indivisible particle. Now, as chemists, our primary goal, the primary thought process as a chemist is to think about matter, not in terms of its bulk behavior, but rather looking at matter from an atomic or micro scale perspective. And by understanding the small subatomic particles that make up matter and the atoms that make up matter, we can understand and rationalize the properties of matter. Okay, so matter is composed of fundamental particles called atoms. Now, atoms can be classified as belonging to different elements, and each element has a unique symbol. The main thing I want you to keep in mind right now is that atoms of different elements have different properties. Now we can take atoms and we can bond them together to form what are known as molecules. Now molecules are composed of two or more bonded atoms. And a critical idea in chemistry is this idea that the atoms that make up matter determine the properties of matter. So let's look at an example of this. So hydrogen peroxide, H2O2. It's a disinfectant. It's not safe to drink. So we can write H2O2. We have 2 hydrogens and 2 oxygens. So H2O2 is composed of a certain number of atoms of different elements. Water, which is written as H2O, has a different number of atoms bonded together. And water, as we all know, is safe to drink. So the key idea that I want you to remember, the atoms that make up matter determine the properties of matter. So as chemists, we're going to look at things from the atomic and micro scale perspective to understand the bulk perspective, the behavior of matter that we see and we interact with in our day-to-day lives. Does this idea make sense to everyone? Is everyone comfortable so far? So just as a recap, chemistry focuses on the study of matter. anything that takes up space and has mass. Matter is composed of small fundamental particles called atoms. Atoms can have different properties if they're from different elements. Molecules are composed of two or more bonded atoms. And depending on the atoms that make up matter, the properties of matter change. A key example, hydrogen peroxide has very different properties than water. So this is an introduction to the thought process that chemists use. We look at the subatomic and the fundamental atomic composition of matter in order to understand the behavior of matter. Is everyone okay so far? Can I get some feedback in the chat? Is everyone comfortable with this idea so far? Okay, perfect. So let's now move on and let's discuss the scientific method. How do we go about investigating the world around us? How do we go about making sense of the world around us? So the scientific method fundamentally is based on observations. And as human beings, we're constantly taking observations of the world around us. Observations can be in the form of collected data, quantitative. I want you to think when you hear the word quantitative, numbers. Another example of an observation would be a description of a phenomena. We call these qualitative observations. An example of a qualitative observation would be, for example, the chair is blue. So it's something that we can't put exact numbers to, but nonetheless is an observation about the world around us and the matter that we interact with. Okay, now a key feature of observations is that they do not attempt to explain the collected data or phenomena. Observations are simply what data have we collected, what phenomena has occurred. So let's look at an example. So in the classic experiment that we've often done in elementary or middle school, we have a balloon. So we have a balloon at room temperature. And if you've ever decided to, as a kid, place a balloon inside a freezer, let's take some observations. We have some pictures of a balloon at room temperature and a balloon in a freezer at 0 degrees Celsius. So let's try to answer some questions. What do we observe about the balloon at room temperature? Is it large? Is it small? What do we observe about the balloon? So initially, what do we observe about the balloon at room temperature? And don't worry, there's no wrong answers here. When you look at this balloon, what do you observe? What do you see about the balloon? Yeah, so one observation is that the balloon is large or larger. Okay. What do we observe when we place the balloon in the freezer? So if we compare these two balloons in the freezer, what do we observe? So the balloon in the freezer, what do we observe about it? Yeah, so the balloon is smaller. Okay, so we've taken some qualitative observations. If we wanted to take some quantitative observations, we can measure the volume of this balloon and say the volume is 250 milliliters. Don't worry about that for now. We can also take another quantitative measurement and say that the volume in the freezer is 200 milliliters. So we can either take a qualitative measurement or a quantitative observation. Now, a series of similar observations for a set of phenomena leads to the development of what is known as a scientific law. So once we start to see trends in our observations for a phenomena, we can begin to develop a scientific law. And now what a scientific law does is it provides a summary of past observations, and it provides a prediction of future observations for a system. Now, the scientific law that best describes this balloon example is what's known as Charles' law. Now, you don't have to memorize exactly what Charles' law is. I'm just showing you that from observations and from our collected quantitative and qualitative observations, a scientific law can be developed to explain that phenomenon. And what Charles' law says is that as the temperature of a gas decreases, the volume of a gas decreases, okay? So as we've seen in our balloon example, at high temperatures, we have a big balloon, a large volume. At low temperatures, our balloon has a smaller volume. Our balloon has shrunk. So let's do an experiment now, and let's pretend we have a new balloon. Let's pretend we have a new balloon at room temperature. And let's say that instead of putting it in the freezer, we're going to put our balloon in ice water at 3 degrees Celsius. Well, let's do 0 just to be sure. So if I wanted to place my balloon into ice water, following Charles' law, based on our previous observations for this gas system, what would we expect to happen to the balloon if we put it in ice water? We would expect it to shrink. Exactly right. We expect the balloon to shrink. And this really showcases the power of a scientific law. From our previous observations, we can generate a summary of our observations, and we can use our previous observations to begin to predict what would happen in a new system. We were able to predict that this balloon, when we place it in ice water, would begin to shrink. It would have a smaller volume. Exactly right. Okay. Now, from observations, scientists can also formulate what is known as a hypothesis. Now, a hypothesis is very different than a scientific law because a hypothesis attempts to provide an explanation for the collected observations. So a hypothesis provides predictive power and is testable via experimentation. It's testable via experimentation. Okay. So an example of a hypothesis in this case is that the balloon contains small gas particles that move and impact the balloon's surface with a force based on the temperature. So our way of explaining why the balloon expands and shrinks is we can say the balloon contains these small gas particles that are hitting the walls of the balloon, and depending on the temperature, the particles either push the walls of the balloon out as they're hitting the walls with a greater force, or they contract as the gas particles hit the walls of the balloon with less force. You don't have to worry too much about this specific hypothesis. More the idea is that the hypothesis tries to explain the collected observations, and it provides predictive power, and we can test our hypothesis via experimentation. So what is an experiment? An experiment is a carefully designed procedure aimed to refute aspects of a hypothesis or provide supporting evidence for a hypothesis. Now, a hypothesis can be revised to account for collected data and observations, or it can be discarded if it cannot be reconciled with collected observations. So in many cases, as we'll look through the history of many cornerstone experiments in chemistry, many of these experiments have resulted in the modification or overturning of previous hypotheses in terms of atomic structure and chemical reactivity. So it's really key to note a hypothesis can be revised or overturned based on experimental data and observations. Now, a well-supported hypothesis becomes the basis for what is known as a theory. Now, a theory serves as a model for the way that nature is that tries to explain what nature does and why. It serves to explain natural laws and observations. So, for example, kinetic molecular theory explains the observations of gas behavior under the ideal gas law. And what kinetic molecular theory essentially states is that gases are comprised of small atomic and molecular species that move in random directions with a velocity based on the gas temperature. Okay, so this kinetic molecular theory helps explain why at low temperatures, as the gas particles are moving less rapidly, they're hitting the walls of the balloon less frequently, and the balloon shrinks as a result. Don't worry about the specific example. It's more just to showcase this idea of how we can go from observations, we can take a series of observations and look at a law. We can also try to explain our observations using a hypothesis. And once we've collected a large amount of experimental data, we can begin to propose a theory, which is a model that helps explain the natural laws and observations. Any questions so far? Any questions so far on this idea? So the main distinction between a chemical law and a theory is that a theory tries to explain, while a law provides a summary of our observations, and it has some predictive power as a result. Everyone comfortable so far? Any questions so far? Okay, so let's talk next about scientific notation. So let's talk about something that's going to be very practical when you're writing reports and dealing with calculations in science. So science is based on observations. Now, we collect data by taking measurements using tools called instruments. Now, when you take a measurement, there are two major components. We have a number and a unit. Okay? Now, we're going to focus first on the number part of this measurement. So when handling numbers in science, we often have to deal with very large or very small numbers. Atoms are very, very, very small. So if we're talking a lot about atoms, we have to often use very small or very large numbers. As a result, we use scientific notation. Now, scientific notation is of the form blank times 10 to the n, where this number that you fill into the blank is a number that is greater than or equal to 1 and less than 10. Now, after this blank, we have times 10 to the n. N can be any whole number power. What do I mean by whole number? No decimals. So you can say 1, 2, 3. You can even say -1 or even -4. As long as you don't have a decimal for n, you're good to go. N can be negative or positive. Okay, so let's look at some examples. Let's look at some examples of numbers in scientific notation. So, just to check that everyone is following along, would 1.0 times 10 to the -4th, would that be okay in scientific notation? Is this an acceptable way to write a number in scientific notation? Yeah, so this is okay. Why? First and foremost, this number 1.0 is equal to 1. Okay, so it's greater than or equal to 1 and it's less than 10. Oops. Second, looking at 10 to the -4th, this number is a whole number, so we're good to go. Let's look at another example. If I have 15 times 10 to the 3rd, is this an okay number in scientific notation? Is this a reasonable depiction in scientific notation? No, it's not okay. Would someone like to explain why? Why is this number as written unacceptable in scientific notation? Greater than 10, exactly right. This 15 is greater than 10. So this is not correct in scientific notation. 15 is greater than 10. So that doesn't follow our guidelines. Okay, what about 0.1 times 10 to the -3rd? Is this a reasonable number in scientific notation? No. Yes or no? I see a lot of students answering no. It's not okay in scientific notation because if we look at 0.1, so thinking about 0.1, if we compare, is it between 1 and 10? Is 0.1 between 1 and 10? No. 0.1 is less than 1, so it's not okay. Okay, let's do one more. What about 1.6 times 10 to the -0.5? Is this okay? Is this a reasonable number in scientific notation? I see a lot of no's. Would someone like to explain why? It's not a whole number, exactly right. This is not okay because 0.5 is not a whole number. You do not want to have a decimal in your exponent. Perfect. Now let's talk about exponents because it's really important to understand how they work in order to perform calculations involving exponents. So you have two components of an exponent expression. You have a base and you have your exponent. Now, when dealing with exponents, you multiply the base by itself n times, where n is your exponent. So for example, if your exponent is 2, you have 10 multiplied by itself, so that we have a total of 10 times 10. You have 1, 2 of your base. Let's do another example. What would 10 to the 5th look like? How many 10s do I need to multiply together if I have 10 to the 5th? 5. So I'd write this as 10 times 10 times 10 times 10 times 10. 1, 2, 3, 4, 5. Does that make sense to everyone? Perfect. Now, there's a trick. For powers of 10, you can move the decimal point n spaces to the right if n is positive. So for example, if we have 10 to the 7th, I'm going to write this as 1.0 times 10 to the 7th. And what we can do is we can take our decimal point, and if we're multiplying by a power of 10 that's positive, all we have to do is move our decimal point to the right n spaces. So I'm going to move my decimal point 7 spaces to the right because I'm multiplying by 10 to the 7th. So I add 1, 2, 3, 4, 5, 6 zeros. So 10 to the 7th would be equivalent to would be equivalent to 10 million. Does that make sense to everyone? Is everyone comfortable with this shortcut? Now let's look at negative exponents. So negative exponents, you can think of a negative exponent as dividing by a positive exponent. So for example, 10 to the negative third can be written as 1 over 10 to the positive third, which we can think of as 1 over 1,000. Now, you can enter this in your calculator and you get 0.001. But again, I have another trick that can help you deal with multiplying and dividing by negative powers of 10. When you're multiplying by a negative power of 10, you move the decimal point n spaces to the left if n is negative. So for example, 10 to the negative 5th, I'm going to write as 1.0 times 10 to the negative 5th. And now what I'm going to do is I'm going to move my decimal point to the left 5 times. So I have 1.0, and I'm going to move my decimal point 1, 2, 3, 4, 5 spaces. And I'm going to add 1, 2, 3, 4 zeros. And that gives us 10 to the negative 5th is equal to 0.00001. Does this make sense to everyone so far? Any questions on this idea so far? So, as we're at the end of our first lecture period, what we're going to do is we're going to stop here for today. So I'm going to stop the recording.